right, everybody, welcome to the Advanced Computing webinar series. Our speaker today is Madhusan Gujral, who's our bioinformatics lead at SDSC. Madhu holds a PhD in structural biology from the Indian Institute of Science. He's currently the bioinformatics lead at SDSC and associated with the UCSD School of Medicine. Although his background is in structural biology, he transitioned to the field of informatics over 20 years ago. Madhu began by developing client-based LLMs for a distributed biological project with users across the US. This was followed by a larger project creating complex pipelines for metagenomics research. Currently, Madhu is conducting performance evaluation and benchmarking of LLMs, fine-tuning with domain-specific data sets. He's also testing and evaluating high-performance LLM inference tools such as VLLM and TGI within a range of current generative and multimodal models. For the past 2 years, he's focused on learning and benchmarking fine-tuned large language models on Gaudi hardware, which is the architecture of our Voyager machine. So I want to point out we are welcoming questions. You can enter them into the chat, and we'll address all questions at the end so that Madhu can just present all of his talk in one large chunk. With that, I'll turn it over to you, Madhu. You can start sharing screen, and you're in charge.
Hello, my name is Madhusudan Gujral, and thank you for coming to listen to me. I appreciate it. The presentation is about fine-tuning large language models with the domain-specific data set. The flow of the presentation is slightly altered. I will start with Voyager and Kubernetes, go to LLMs, then go to the LoRA fine-tuning demo, because I feel demo is very important because it has too many moving parts, and I feel that's where people would need a holding hand. And I need to make a hard stop at 50 minutes past the hour, and depending on how much time is left, I would cover the conceptual and theoretical side of parameter efficient fine-tuning with LoRA. And then there'll be some time for QA session. Before I go further, in the chat, I've listed the directory where I have put all the libraries, scripts, training data, instructions that you would need to get started on Voyager to launch fine-tuning. It's in a folder called /10, and there is something April. Please copy all those files to your home directory on Voyager if you have a Voyager account. So let me start. There are two types of models, text generation models hosted on Hugging Face portal. They fall into two broad categories: pre-trained or base model and instruct models. Instruct models have a IT or instruct as a suffix at the end. And the base models and our pre-trained models have been trained with vast amounts of text data and some amount of label data through extensive training process, and their weights are generated. On the other hand, instruct models are generated from the pre-trained models, but they're further fine-tuned with vast amounts of instruct data sets in the form of prompts and responses. They could range from anywhere from hundreds of thousands of prompts to tens of millions of prompts to generate an instruct model on the Hugging Face portal that they exist. And that needs fine-tuning of all the weights, all the parameters. It's very resource intensive. On the other hand, for LoRA, that what we'll be doing in our presentation, the base weights are frozen, they are not altered. So we'll be creating the separate adapter matrices on the side called A and B matrices, whose weights are updated during fine-tuning. And it's very light on resources, parameter efficient fine-tuning with LoRA. And at the end, you will see that that the adapter weights are very tiny fraction of the model weights. It constitutes only about 0.1 to 2% of the entire model weights. And in the end, one has the option to add the adapter weights, LoRA adapter weights to the original model weights, but that depends on the use case. Now, the demo I'll be giving, it will be on Voyager. Voyager is a Kubernetes cluster. Its hardware is acquired from Habana, which is owned by Intel. And the basic promise of Voyager is to give access to innovative AI hardware for people who are carrying out their work in deep learning. We are in the 4th year of operation. Initially, uh, the Habana software stack that was provided to us had a support for both TensorFlow and PyTorch, but the support for TensorFlow was discontinued. So the only support that we have with the Habana software stack is with PyTorch libraries. This is a snapshot of the user guide that exists for Voyager at SDSC website. And you can see that it has 42 first generation Gaudi 2 nodes. Each node has 8 cards. The memory for each card is 32 gigabyte video RAM. And total number of first generation Gaudi cards are 8 times 42, 336. About 4 months ago, we received 40 second generation Gaudi nodes, or Gaudi, they're called Gaudi 2 nodes from Habana as a gift. And 20 of the first generation Gaudi nodes on Voyager have been replaced with 40 second generation Gaudi 2 nodes. This is the layout of a one Gaudi card from first generation. You see that 60 nanometer process technology. It's a measure of how tightly the electronics is packed on the card. The first generation Gaudi 1 cards have 8 TPC cores, tensor processing cores. They have a matrix math engine. Each card has a 32 gigabyte of video RAM, or it's also called high bandwidth memory. And the Ethernet speed is 125 gigabyte per second. That is a data transfer rate from one Gaudi card to another Gaudi card, whether it's in the same node or it's in a different node. This is the layout of Gaudi 2 nodes, or second generation Gaudi nodes. The process technology is 7 nanometer, which means that the electronics on this card is packed much more tightly, which means that there are more transistors in the same physical space. That also means that more computation can be done. However, power requirements are also substantially more, and it generates more heat. And that's the reason that only 20 Gaudi first generation nodes could be replaced with Gaudi 2 nodes. Gaudi 2 nodes have 24 TPC cores. They have a dual matrix multiplication engine, and the Ethernet data transfer speed has jumped from 125 gigabyte to 300 gigabytes. And the video RAM on each card is 96 GB. And the static RAM on Gaudi 2 card is 48 megabyte. It may not seem like very large, but it's very useful. Now here is the performance numbers, are the architectural numbers for three generation of Gaudi cards. Voyager doesn't have any third generation Gaudi card as such, but we were given access to it briefly for benchmarking and performance evaluation. You can see that the video RAM per card has increased from 30 gigabyte on the first generation Gaudi cards to 128 gigabyte. That number of TPC cores have increased substantially. The data transfer rate, the HBM2 bandwidth has increased from 1 terabytes per second to 3 terabytes per second. And the SRAM has gone from 24 megabyte to 96 megabyte. I want to point your attention, this SRAM is not very big, but it sits on the GPU. So the data transfer rate from SRAM to GPU is even more than the HBM2 bandwidth that you see here. So if people can find a clever way of making use of SRAM, things can really speed up. And I just want to mention that this SRAM is used in flash retention. You might have heard this name. Now coming to the Kubernetes, when you connect to the Voyager, you must execute this command module load Kubernetes to get the Kubernetes commands become available to you. The first command, you need to launch a pod. You need a YAML file or a JSON file. go with this kubectl apply -f and your YAML file name. And most people on Voyager are assigned to a location and they have a namespace associated with it. And they must provide the namespace to launch the pod. And there are other Kubernetes commands listed here. If you want to see which pods are currently running, you can type kubectl get pods -o void and your namespace. And if the pod has completed the life cycle, you can delete the pod with kubectl delete command. And there are additional commands and cheat sheet. I have provided the link. This is actually my YAML file that I'm sharing here. This is what I use generally, something like this to launch a pod. The kind is pod. And I give a name to a descriptive name. So I'm doing fine tuning, and this is a Synapse AI version I'm using. I'm requesting 8 cards on Gaudi 2 node. And you see the tolerations in the YAML file, the toleration tag. It's telling the YAML file, it's telling the Kubernetes cluster that I'm requesting that I want to land on a Gaudi 2 node, not Gaudi 1 node. And then there is an affinity tag below that. And it has a number 121, where I'm telling Kubernetes that I want a Gaudi 2 node, and I also want Gaudi 2 node that is hosting driver version 121. And then you will have volumes listed on the right side at the top. And this is a storage space that I want to use. And all the Kubernetes, for the Kubernetes, one needs to have access to the Docker container. And here is the Docker container, which contains the essential software stack from Habana with PyTorch libraries. Here is this image that I'm pointing to. And the storage space, the volume I defined, they must be mounted. They should be mounted within the container, and that's done with this volume mount stack. And under the resources, I'm just pointing out how many Gaudi cards I need. I'm requesting 8 Gaudi cards. And then there is this huge pages 2MI. This 2MI refers to 2 mega, actually refers to 2 mega maybe bytes, but actually for our context, we can take it as a 2 megabytes. And that's 9500 MI is the entire memory of a single Gaudi 2 card. So I'm giving instruction that the entire memory of the Gaudi card should be split into the blocks of 2 megabytes. So that way there'll be 47,500 blocks roughly. The idea of this breaking the memory into blocks is to effectively make use of non-contiguous memory on the card. And that is also used in the operating system, and it's called page detention. It's the same concept borrowed from the operating system lingo. And then the bottom, I'm passing a command to the pod that go to sleep for an hour because I want to use it in interactive mode. So I'll be using the Llama 3.18 billion instruct model for fine tuning. Just to keep a peek under the hood, this model has a vocabulary of 128 tokens, and each token is represented as an embedding of 4096 dimensional factor. And the model consists of 32 transformer blocks. Each block has a attention layer and a feed-forward network layer. And each attention layer has 32 attention heads. So the number 32 blocks and 32 attention heads per attention layer, it's just a coincidence. Other models can have different number of attention blocks, and their number of attention heads per layer they don't need to match with the number of transformer blocks. It's just a coincidence here. Now, what's there in each transformer block? Let's have a look. As I mentioned, there are 32 transformer blocks. Sometimes they're called layers. People have used the terms interchangeably. And the model in total has 226 linear layers. Let me see how we come up with this number. In each attention layer, there are 4 projections: query, key, value, and output. They are linear projections, but essentially they are weight matrices. And each feed-forward network layer has 3 projections: gate, up, and down. So there are 7 projections per transformer block. So we have 32 blocks. If you multiply 7 with 32, you get 224 linear layers. And then there is a one output layer and there's a one input or embedding layer. So if you add them up, we get 226 layers. And now let's figure out how do we come up with this number 8 billion. There are 32 blocks. The hidden dimension or the embedding dimension for each token is 4096. But when you go to the feed-forward network layer or multi-layer perceptron, the, the dimension is 14,336, which means that this is the number of perceptrons in that layer. As I mentioned, the vocabulary of the model is 128K. There are 32 attention heads per attention layer for queries. But for keys and values projection, there are only 8 heads. I will show that in a separate slide. Why there are 8. So, but if you look at the head dimension, so it's for query, it's 4096 divided by 32, that's 128. But for keys and values, the dimension is reduced, 1024, and there are 8 heads. So the head dimension, even for K and V, is same, 132. Oh, sorry, 128. Now each layer has 4 projections. They are nothing but weight matrices. And now let's look at the query weights. So it has a dimension of D model, which is the embedding dimension, number of query heads, the head dimension. They again NQ and DH add up, multiply to 4096. There are 16.7 million parameters in the query weights. And for key and value, there are 2 of them. So there's a number 2. Dimension of the model, number of KV heads is 8. Head dimension is same as 128. We come up with a number close to 8.4 million. And number of the parameters in output layer is same as the query, 16.8 million. If you add them up, so we are a little short of 42 million here. Let's look at the what's happening at for the weights in the feed-forward network layer. There are 3 projections, and each projection has weights of the same size, 4096 times 14,336. And if you multiply, you get over 58 million parameters. There are 3 projections there. If you add them up, it's 176 million. So if you multiply the weights from attention layer and the feed-forward network layer and multiply with 32 blocks, we get about 7 million. As I mentioned, model has a vocabulary of 128 million tokens. Multiply with the embeddings, it's over 500 million. And at the output layer, the reverse event happens. So another 500 million plus parameters. If you add them up, we come up with 8 billion parameters. As I mentioned about the group query attention, etc., in the past, each attention had its own query, key, and value weights. There are 32 of them. I'm just showing 4 here. But fast forward, things changed. People found out that we don't need separate key and value heads. Instead, 4 query heads can share the key and value heads. That saves memory. Group query attention is an approximation to the multi-headed attention. but it's a very close approximation. But it saves a lot of memory on the video RAM. That's the idea of switching to GQA. People don't need to do anything to uh, take benefits of GQA because it's a part of models architecture. Now let's take a look at a case when the prompt is given to a large language model. Here is a prompt. Data visualization empowers users to, and its model is supposed to predict the next token. First step is the tokenization of the input prompt, and you can see that the empowered word is broken into two tokens. And then there is a next step is embedding. Each token has an ID in the model, and you can fetch that particular token's embedding from the model. It's 4096 dimension vector, and it's fetched for all the tokens. Then there is a rotary positional embedding because each token has a position in the prompt, and it's important. And positional encoding is also the same dimension as 4096. They are combined together for each token. And at this level, at the fourth point, when they're added, we are not ready to go to the attention layer as such because the, the, the embeddings for each token must be normalized, and it's normalized with the root mean square value shown here. And once the embeddings for the tokens are normalized, then flow is ready to go to the attention layer. Here I have taken a picture from an article. I think I have put the link here. And there is a prompt. The phone was on the table and it. So there are 8 tokens, and the embedding of each token is D model, that is 4096. So this matrix here is of the shape 8 times 4096. And now we have the weights for query, key, and values. Look at the dimensions. When we multiply this prompt matrix with query, key, and values, what's happening? D cross N. Weights have dimensions of D model times DH. H is a head dimension. So we get the query matrix, keys matrix, and values matrix. Their dimension is N times DH. To get the attention scores, we multiply the query matrix with the transpose of key matrix to get the raw attention scores. See, the matrix has changed. Now it's N times N because when you multiply query with the transpose of keys matrix, you get it. The raw attention score matrix, which is of N times N. N is a number of tokens, input tokens. And these are called the raw scores. And I've just given a formula for the softmax function here. Now it's a continuation of the previous slide. We stopped here in the previous slide. Attention scores, we need to get the weighted attention scores. For that, we divide the attention scores with the square root of the head dimension. Head dimension, I've used term DH or DK, but it means the same thing. And the weighted attention matrix is of the same form, N times N, and what it contains is the attention scores have been converted to the probability. And once you multiply these probabilities with the value matrix, we get a context matrix for a head, and it's basically given by the formula at the bottom right side of the slide, and its representation is Z. Then the same calculation is performed for all attention heads. Then the information from each head is concatenated. So what is happening in this attention mechanisms when we give it a prompt? Attention layer is trying to figure out which noun is attending to which verb and which adjective is described describing which noun, and what kind of syntactic semantic relationship exists among the tokens. It's trying to capture all the information. Could be, uh, could be liking, disliking, hate, whatever uh, the uh, the behavior that comes into your mind, it's trying to capture. It could be uh, proximal, distal, space and time, platonic, whatever possible. It's trying to capture everything possible uh, in the attention layer. And what it comes out of from this attention scores at the end, we have a combined context vector once you concatenate all the context scores from each head. And the benefit of multiple heads acting is that each head is looking at the different facets of the same prompt. And then the information is concatenated. And this combined context matrix is multiplied with output matrix, and that's finally the final output of the attention layer. This is another example. I've taken it from another YouTube video. Suppose there is a prompt. Apple released a new iPhone model last week. Models have no clue about what is being referred Apple here. What is the context of the Apple? From models perspective, Apple's embedding is close to the other fruits like orange and banana, etc. Because most models have only one embedding for word apple. Now, if this is the query matrix for the prompts, and if this is the key matrix that we have already generated, and we multiply the first row corresponding to the apple with the transpose of key and get the attention scores, then apply scaling and the softmax, we get the probabilities just for the first row. You can see that the scores for Apple attending to Apple itself and Apple attending to iPhone are much higher compared to the other scores in the row. I mean, it's shown as a matrix and as a column, but actually it's a row. So when we apply this first row with the value matrix, you would see that the elements which get multiplied with this first element and the element corresponding to the iPhone get more weight. So you can see that the Apple and the iPhone are controlling the weight, uh, and that's how the context is being built. So the final vector that we get from this, just the first record, first row, we get the context of this Apple or its embedding has changed. Now it's closer to the device in a embedding space compared to when it started, it was closer to F2. So that's how the attention is built. So then there is a constant debate whether one should do fine tuning or one should do RAG. I won't go into it, but I will just point out one thing, and that is RAG is fine as long as your prompts are very short, because once you give your documents to RAG, they are broken into pieces. They're converted into vector embeddings. They are stored in a vector store. When you give a query, it tries to see where the query embedding matches with the embeddings that exist in the vector store, and it gives the responses back. And it gives you various responses back depending on the relevance. The question is that it works fine as long as your prompts are simple. But once the prompts are convoluted such that the response to a prompt, the answer sits in various different documents, at that time, you start to get very choppy answers. And that's like the question complexity. It struggles to give you a good answer. It gives you many broken answers. On the other hand, when the model is fine-tuned correctly and you're satisfied with the fine-tuning, it gives you a much better, coherent, holistic answer. And the idea of fine tuning is for the model to generalize what it has learned. So it can give you a complete answer, not a fragmented answer, unlike RAG. With that, I would stop and I would go to the uh, to the actual demo. Oh, actually, uh, let me show a few more slides. Okay, to start fine tuning of an LLM, what we need? We need access to a model. We need training data. We need libraries to facilitate that. We need software tools to actually do the fine tuning. And we need Hugging Face tokens because most models are hosted at Hugging Face portal. So for that, you need to create an account on Hugging Face portal to access the models. You need to go and create a Hugging Face key for your own use and need to create the model specific API keys for the models that you want to use. And in addition, you also need to get approval from the model's vendor. This is my shell script that I use to fine tune a model using LoRA PFT on Voyager. And here I'm saying I want to use the Llama 3.18 billion model. Here is my training data, train file. The training data can be on the Hugging Face itself. You can point it there, that's fine. Or you can fetch the data from Hugging Face and you can have it on your local directory. Uh, and this is a name of the output folder. I like to give descriptive names. The data I'm using here is called Bolt Monkey data. It's a psychology data set. And it has about 392,000 prompts and responses. I'll be running only one epoch. Uh, at the bottom, I will be splitting the data. You can see the validation split 10%, 90% data for training, 10% for validation. My LoRa rank, I'm setting at 64, and LoRa alpha is also 64. We can talk about it when I talk about the conceptual side of LoRa. This is the learning rate. Uh, this is the scheduler type cosine. What it means is that as the fine tuning is progressing, the learning rate is being reduced and it follows a cosine curve from like cosine curve going from 0 to pi by 2. Like it starts at a value 1, I mean, one just a scale, um, then it drops down to 0 gradually as the fine tuning progresses. And this is the learning rate. My batch size is 2 for learning. And I'll be adjusting the weights of all the projections, 7 projections listed here. I've listed all of them. And this is the alpaca data. You can see the URL here. This data is in the form of a prompts and response. The instruction is the prompt. Response is the output. Input can be empty, but generally it's a context. For most situations, there is no need. That's why it's empty. But if you look at it, identify the odd one out, I need to give the context, what I'm referring to. Twitter, Instagram, Telegram, and Telegram is the outlier. The last column is not important. I'm not showing the Bolt Monkey data here. That's also available at Hugging Face portal. The reason is that the software script that we have, it likes the data column header in the form of instruction, output, and input. Bolt Monkey data has different column headers. So I had to fetch the data in a JSON format, change the column headers, and convert it to Parquet on my on my machine. And that's why I'm using bold monkey data from my Voyager home directory. With that, I'll stop sharing my screen. Okay, so you can see the bold monkey data. This is the training data, psychology data set. I have left the detailed instructions how to launch the fine tuning, what files you need in this Word document. Um, and these are the optimum Habana libraries. These are libraries. They are created by Habana and Intel team, Habana and Hugging Face teams. This is the library which has all the software scripts that you need. Um, and this is my YAML file I just shared with you. And this is a script to launch the shell script that I showed you to launch the fine tuning on Voyager. And there are also two shell scripts that is to launch model for inferencing in a standalone mode and also with the adapter weights that you obtain with parameter efficient fine tuning. They are listed as test. They're starting with test. And before you can launch fine tuning, you need to launch the YAML file, as I mentioned, launch the pod. I have already launched the pod here and it's taking time. Okay, you can see my pod is running here. And on this side, I'm already connected to the pod. And on the other window, but when you, okay, here I'm connected to the pod. And I needed to, before I could proceed with the fine tuning, I must define some environmental variable. My home directory, this is a second one, which is a HF home. That's where the model would be stored once I fetch it from the Hugging Face. Once you define the model you're interested in the script automatically goes and fetches the model for you. You don't need to do anything for that. So this is the place where the model would be stored. And you need to define the Python path for the optimum Havana libraries. These libraries are interface between the transformer library and the Havana hardware. And you need to define the path because there are some binaries you need that that are also provided with optimum Habana. Then you need to set up the Hugging Face command line interface, and that is your Hugging Face token. I have put it as XXX. Export Hugging Face token. That's another way of exporting it. And then you need to provide the Hugging Face API key for the model because most models on the Hugging Face portal are gated. Not all, like Quen models are not gated. So are I think some of the IBM models are not gated. And recently, some of the Microsoft models are also, they have lifted the gate on them. They are access to available to anyone. But Llama models and Google models, Gemma models are gated. So I'm in a folder where I have all the necessary scripts. And this is the shell script I shared with you. I'm will be fine tuning this model. Let me launch this script. Oops. So I'm launching it in interactive mode. So whatever commands I'm passing in a command line mode, all these commands can be copied in a YAML file. That way you don't need to connect to the pod and launch it manually, but I'm just giving a demo. So you will see that the pod is, the script is launched. I mean, it's running. I will let it run. Uh, I've already run a similar script. Last night. So let me show you how the output looks like. Oops. So this is the standard output looks like for the Voyager fine-tuning run, and I can see at the bottom the evaluation matrix. This is for the 10% of the data. This is the evaluation loss. It's the measure of this is the perplexity, and this is the evaluation accuracy. It's 84%. And if I go up, I see the same numbers for the training. I ran one epoch. 90% of the data was used for training. Training loss is 0.74, and the train runtime was 11 minutes. So you can see that the parameter efficient fine tuning is really, really fast. And even if I'm using all the 7 projections, it's with the LoRA rank 64, it still gets done under 20 minutes.
Madhu, you're at 11:45 time.
Okay, thank you. So you can see that I'm using all the 8 Gaudi 2 cards for fine tuning. I'll go back to I'll stop here and I'll go to remember, you need to create your own account to fetch a model from the Hugging Face portal, because model is not provided in that folder that I shared with you, which has all the information except the model. Okay. So once the fine tuning has completed, it generates a output folder. Output folder also has all the information that you uh, that you saw in the standard output. And if I install a tensor board with pip command and fetch the output folder on my local machine. Actually, you can even do on Voyager if you use Jupyter notebooks. But I fetch it on my local machine, my MacBook. And then I pointed the tensor board command to this folder, output folder /runs. And then it brings out uh, the entire layout of all the parameters, how they were changing during fine tuning. Here is the evaluation accuracy, what's happening to it after one epoch, 2 epochs, 3 epochs, then it starts to drop down. So I should have stopped after 3 epochs. Here is the learning rate I mentioned, that it follows a cosine curve. You see that here it's following the cosine curve. You see a dip, and that's because because even though there is a learning rate that is specified in the script, but for first 3% of the data, the learning rate is really, really, really tiny. And the idea behind it is that um, to make sure that the gradients don't blow up. And I think this is the training loss, how it is dropping, you can see. So there are a whole bunch of matrices that you can view, but you need to install tensor board for that. As I mentioned that we had access to the Gaudi, we have access to Gaudi 1 and Gaudi 2 nodes on Voyager. We did have access to Gaudi 3 for a brief time. This is the performance run for this particular model with the Bolt monkey data. And if I just give one card on Gaudi 1 node, it takes 245 minutes. When I use all the 8 cards, half an hour. And if I employ flash attention, it saves about 10% of the time. And on Gaudi 2 nodes, they're about 3 to 3.5 times faster than Gaudi 1 nodes for this fine-tuning purpose. And Gaudi 3 nodes are again about 2 to 2.5 times faster than Gaudi 2 nodes, you can see here. And sometimes there's a question where you want to draw a line between parameter efficient fine-tuning, or you want to do a full supervised fine-tuning. So this is a picture from that article, LoRA Without Regret. You can see that it's rank 64, LoRA rank 64 with parameter efficient fine-tuning. The results you get are very close to full fine-tuning, which is very resource intensive, by the way, because there you're altering the weights of every weight in the model. Now let me see if I can spend a few minutes on the conceptual side of the LoRA. Okay. So this is the pictures you might have seen in various articles. The multi-headed attention. This is the regular transformer blocks stacked one over the other. And in the forward pass, the LoRA is introduced. That's nothing but two side matrices called adapter matrices A and B. They are of rank R times D. D is a more embedding dimension. R is the LoRA rank that you choose. And other matrix is, or the form, it's transpose. I think I have a better way of explaining it in the next slide. Maybe let's go here. So these two matrices in the forward pass, we go. It's the same representation here. The slides, the labels are messed up here. So delta W are those LoRa adapter weights. So when in the forward pass, initially, one of the matrix A has random values, very small random values from negative to positive, but they are fraction of 1 and they're centered around 0. The matrix B is all 0. So when you multiply A and B, initially the product is 0. So when you start fine-tuning, you have the original weight, they're frozen. You have the LoRa weights. In the beginning, they're not contributing anything. So a batch of data flows through all the 32 transformer blocks. And at the end, the loss function is computed for the training data. And in the back propagation, the optimizer updates the weights of these LoRa matrices. And that happens for all the data goes through the entire 34 blocks batch-wise. And the weights are constantly, adapter weights are constantly updated. And if you look, that's what is happening here. I think the layout is messed up. I don't know why. So for example, if my LoRa matrix is of the form 8, if my rank is, okay, let me go back. X is the embedding vector. These are my prompts. If I give 8, If my prompt has 8 tokens, my information is going in the form of a matrix 8 by 4096. Here is my weight matrix, that is the form 4096 times 4096. Here is a matrix. Here R is the LoRA rank that I've assigned times 4096. B is its transpose matrix wise. So you see that when I'm multiplying here my input matrix with original weights plus input matrix with LoRA weights, what's happening to the matrix? First, I multiply X with B, X with B. So I get, shown here, I get a matrix of the form 8 times R. Then I multiply 8 times R with A, and A is here. So I get a matrix 8 times D model. So you see that it's a clever way of computing the adapter weights. And there is one more thing what adapters are doing is we are trying to capture the entire variation with this LoRA rank. Because the matrices are of much smaller dimension compared to the original weight matrix. The idea is to capture the entire variation with much smaller channels. Think of it as a principal component analysis. So if you have a feature matrix with 100 elements, you can see if the elements, if the column information there is correlated, you can see that you can perform PCA on it, and you can see that show the entire variation or 90% the variation just by 3 columns. So the LoRA concept is not the same, but it's on the similar lines. You need much smaller adapter matrices. They need to be updated. So once you have the adapter matrices created, everything is fine-tuned. You can merge the adapter weights with the original weights if you need. And many of those inferencing tools like VLLM and TGI give you an option to load the original weights and provide the adapter weights separately. That way you can perform the inferencing with the model and the LoRA weights. Actually, the scripts that I left on the folder that I pointed to, it has 2 scripts. One is to see, to do the inferencing from the model as it is. And in the second case, you provide a model and also provide the LoRA weights, and then you can do inferencing there as well. So here is just a mention which layers you should target. And you can see that if you want the quick results, you can target query and value matrices. That's what described in the original LoRA paper. But that only gives you the contextual adaptation. But you want a knowledge adaptation, you should also use up and down projections. And ideal thing is that you must perform LoRA on the all linear layers. I think with that, I should stop. And I will take any questions that you might have.